Hi, and thanks for watching Best Math Tutors. We're going to look at a question using complex numbers to calculate the total impedance in an AC circuit. And in order to do this, we're going to need to be able to convert between polar and Cartesian form and back again. And we're also going to need to be able to multiply and divide in polar form and be able to add in Cartesian form. So we can see in this example I've got here, we've got an AC circuit. We know that it's an AC circuit because it's got branches in the circuit there. So we can see that at this point the current would split into two. And we've got an impedance Z1, which is given in this complex form. And we've got an impedance Z2, which is given in this complex form. And what we're trying to do is work out the total impedance in the circuit. These complex impedances come about when we've not just got resistances, but we have things like capacitors and inductors as well in the circuit. So in that case, the impedance might not be, and the current which is generated might not be in phase with the voltage supply. So we've got this formula here, and we can see that the top of the formula is Z1 times Z2. So in order to do that, we need to be able to put the impedances into polar form. It's not quite as easy to do a multiplication in Cartesian form. So we want to put that into polar form. And we're going to do this addition on the bottom in the Cartesian form, which it's written here. So we're going to do this bit in Cartesian form. And then when we've got an answer in polar form on the top and an answer in Cartesian form in the bottom, we're then going to convert the Cartesian answer on the bottom line into polar form. And that's so that we can do the division. We can divide top of the fraction by the bottom of the fraction. So we're going to divide the top in polar form by the bottom in polar form, which is easy to do. So first thing I'm going to do is I'm going to try and convert these Cartesian forms into polar forms. So I'm going to change to polar form. So the first step in doing these is always to draw an arc-and diagram. So just draw myself a set of axes here. And I'm going to just represent this Z1 on that one. So if I do that, then I've got 6 on the real axis. So the real is the horizontal axis, and I've got an imaginary, which is also the J-axis. So that's the imaginary part of it, and that's 3. So we can see that representing Z1 on that arc-and diagram, it would be there. There's Z1. And so what I need to work out is this angle here from the horizontal axis. So we need to know that this is the positive direction and this is the negative direction. So theta is given by tan minus 1 of the imaginary part divided by the real part. So in the case of Z1, what we're going to do is we're going to have tan minus 1 of the imaginary part being 3 over 6. I'm just going to get my calculator up and calculate that. So I'm going to need to go shift tan, and then I'm going to use fraction button, and I've got 3, navigate down to the bottom, there we go, and then calculate that, making sure I'm in degrees as well rather than radians is the other way we can measure angles. So if I do that, then what we've got is, I'm going to call that 26.57 if I round it up to 2 decimal places. So 26.57. And I also need to work out the modulus of that. So that's the length of the line, which I'm going to call lowercase r. There we go. So r is given, it's like Pythagoras, this is. So it's the square root of the real part squared plus the imaginary part squared. So in the case of Z1, then that's going to be square root of 6 squared plus 3 squared. So let's again work that one out. So I'm going to do the square root of 6 squared plus 3 squared. And so I get this 3 root 5, and what I can do, that's in exact form, but I want it in decimal form at the moment. So if I press that SD button there, that puts it into decimal form, and I get 6.71 if I round it up to 2 decimal places again. So that means that in polar form, I can write Z1 as being equal to, and I put the modulus first, so 6.71, and then I write the argument, which is the angle, that's this one, 26.57. So that's Z1. I'm also going to need to work out what Z2 is. Let's move the board up a little. So first of all, again, I'm going to draw the arc diagram. Try and do that. There we go. So that's going to be 2 and minus 2. So it goes across by 2 and down by 2. So that would be what our Z2 would look like. That would be there. And what I'm interested in is working out this angle, theta, and this length, r. So again, using that formula, theta is tan minus 1 of the imaginary part over the real part. So in this case, theta is tan minus 1 of the imaginary part being minus 2 over 2. And so if I bring the calculator up and work that out, I'm going to do the shift again, use the fraction button, and it's going to be minus 2 over 2. And there we go, we get minus 45. So minus 45 degrees. And then I also need to work out what r is. So again, using that formula for r, that it's the real part squared. And although, well, the real part squared is a positive number. For the imaginary part, although it's a minus, if we squared a minus, we'd still get a plus. So I might as well just put in plus 2 squared. So if we put that in the calculator, what we're going to get is square root of 2, square button, plus 2 again, press the square button. And that's 2 root 2, but we don't want it in that form. We want it in decimal form. So that's it. 2.83 if I round that up to 2 decimal places. Okay, so that means that Z2 is equal to 6 point, not 6 point, that's the other one. I'll rub that out. So that's going to be the 2.83 as the modulus, and then the angle is minus 45. There we go. So that's the two initial impedances written in polar form. So next thing we're going to do, we're going to work out the top part of this line, this fraction here, which is Z1 times Z2. So Z1 times Z2, so the top part of the fraction. So that means it's the written in polar form is how we want to do this. It would be more difficult if we did it in Cartesian. We could still do it, but actually we want to do this in polar form. And when we multiply numbers in polar form, what we do is, so for multiplication, times or multiply the modulus or moduli, if we're in plural of modulus is moduli, and we add the arguments, which means we added the angles. So if we do that, then that means that this is going to be have a new modulus of 6.71 times by 2.83, and the new argument is going to be the 26.57. I think that says it on there, 57, yeah, 26.57. And then if we add this negative number, it's going to be equivalent of taking it away. I'll just put a plus and minus there, but we can see we're adding a negative number. So adding 45 degrees. And so we just need to work that out. So 6.71 times by 2.83. So we get 18.99, I'll call that. If I round that up to 2 decimal places, 18.99. And then if we're going to add these together, that becomes 26.57 minus 45. And I'll just do this on the calculator just so I don't make any mistakes. So 26.57 minus 45. No, not 45, not 44, 45. So it's given us in this form, which we don't really want. We actually want it in decimal form, so we just press that SD button, and we've got minus 18.43. So that's what the top line of the fraction works out to be. We now need to work out the bottom part of the fraction. So the bottom part of the fraction is Z1 plus Z2. So let me just remember what those two fractions were. Those two is 6 plus J3 and 2 minus J2. So 6 plus J3 was the first one. We're going to add to it 2 minus J2. So we're going to add them together. And when we're adding complex numbers in Cartesian form, what we do is we add the real parts together and we add the imaginary parts together, and we do those separately. So the first part of this is going to be the 6 plus the 2. So we're going to get 8. And then now we're going to do the imaginary part, and we've got 3, so that's a positive 3, and we're going to add to it negative 2. So it's going to be the same as doing 3 take away 2. So we're going to end up with plus J. That's what the bottom part of the fraction looks like. But we need to put this now into polar form. So as you'll notice, there's lots and lots of converting between the different representations of this complex number. So again, we're going to draw the Argand diagram. So we can see this is going to look something like this, where this is 8 and this is 1. So there's the imaginary axis, there's the real axis. And what I need to do again is I need to work out theta and the modulus lowercase r, so that's theta. So theta is going to be tan minus 1 of the imaginary part, so 1 over the real part. And so let's get the calculator up again. So shift tan fraction 1/8, and we get 7.13. I'm going to call that. So 7.13 is the angle, and the modulus again is using that thing that looks a bit like, well, it's actually based on Pythagoras. It's 1 squared plus 8 squared. So calculate up again. So 1 squared is actually just 1, but I'll put it in for to show the method. So 1 squared plus 8 squared, get root 65, and again, I'm going to just press the SD button. So I've got 8.06 is my new modulus, 8.06. So if I want to express this in polar form, so in polar form, it's going to be the modulus 8.06 with the angle 7.13. So there we go. So what we've got next to is we were looking for the total impedance. So we're really close to the end of the question now. And that was Z1, Z2 over Z1 plus Z2. And it was important to, for the purposes of dividing, getting them both into polar form. So the bottom of this was 8.06 with an angle of 7.13, and the top of the fraction was 18.99, with an argument of minus 18.43. So that was Z1 times Z2 gave us that top line there. And what we're going to do then is, because it's in polar form, it's quite easy to divide again. We could again do it if it was both in Cartesian, but it's much easier in polar form. So division in polar form, in polar, is what we do. We divide the modulus, so divide the modulus or moduli, and we subtract the arguments. So it's basically the opposite to what we do when we're doing multiplication, so subtract the arguments. So that means in this case, we've got 18.99 divided by 8.06, and that's our modulus, and the argument is going to be, so that was negative already, so minus 18.43. Minus is because it actually was a negative argument, and then we're going to take away 7.13 from it. So get the calculator up, move that over here. So what we end up with then, if we do the division first of all, so we've got 18.99 divided by 8.06. Oops, what's happened there? 8.06. So that gives me 2.36 if I round up to 2 decimal places. 2.36, and then the new argument there is going to be given by minus 18.43 minus 7.13. So if I clear that off, so minus 18.43, take away 7.13. So if I do that, then that's going to give me minus 25.56. So then the very final step in the question was, if we read back up at the top, was to put it into Cartesian form. So that was the last bit, putting it into Cartesian form. So currently we've got our final answer, but it's in polar form. So let's go back to here. And what we know, just to talk about the way we would do this. So if we can imagine here's our complex number represented in an argand again. So what we've got is a line that's 2.36 in length with an angle of, because it's below the x-axis or the real axis, then it's negative. So that angle itself is 25.56, but it's a negative argument there because we've gone in the negative direction. And when we're converting from polar to Cartesian, then what we do is if we've got something in this form, r and then theta, then what we do is in the Cartesian form, it becomes r cos theta plus j r sine theta. So in our case then, we've got the 2.36 with an angle of minus 25.56. So we're just going to apply that. So in Cartesian then, it's going to equal the 2.36. So just replacing the r there by 2.36 times by cos of minus 25.56, and then I'll just let me move the board across a little. There we go. So and then plus j, so the imaginary component, 2.36 times by sine this time of negative 25.56. So we now need to put all this into the calculator. So for the real part, it's 2.36 times by cosine minus 25.56. So 2.129, so I'm going to call that 2.13. And I'm just going to do the imaginary part, so I need to work out 2.36 times by sine negative 25.56. So I've got to work that bit out. So 2.36 times by sine, and it's negative 25.56. So we get negative 1.018, and I'm going to call that negative 1.02, running up to 2 decimal places. And I've just put that in a bracket because I just need to do something with that bit at the end there. So the minus sign here, I'm just going to bring in front of the j and replace the plus there. That's going to be 2.13 minus j 1.02. And that's it, we've done it. So I hope that's been helpful to you. If it has, please like our video and subscribe to our channel to see more of our videos. Thanks for watching.